So here we have a double integral. We are not given any specific instructions about a particular method to use to evaluate it. I like this kind of problem because you have to synthesize some of these previous approaches that we have been learning about and decide which one is best. I do want to point out that there's not necessarily one correct way to do it here. Right now, I'm going to work this problem using the approach that to me at this current time seems the most efficient. If you do it another way, then that is completely fine so long as we both get the same answer. Now, having said that, what my instincts are telling me right now is to use polar coordinates. Why polar coordinates, you might ask? Well, that's a very good question. Why polar coordinates? Well, because the region of integration that we're given, this wonderful sketch I have here on the left-hand side that looks like half of a donut or maybe half of a bagel, the region of integration is circular. And polar coordinates, region of integration is circular, and polar coordinates are just tailor-made for circular regions. So here's what I mean. In rectangular form, say a circle of radius 10 is going to have the equation x squared plus y squared is equal to 100, right? But in polar coordinates, well, the equation of a circle of radius 10 centered at the origin is just r is equal to 10, which I don't know about you, looks a lot simpler to me. And what do you know? In this region here, we have a circle of radius 10 centered at the origin. So let's see what we can do with that. So before we get into anything too heavy, polar coordinates come with their own host of conversion formulas, and I'm just going to write all of them down here in case they come in handy. One is going to come in handy here right off the bat, or two actually. So we're going to need to convert dA, so that's with respect to a patch of a rectangular region in the xy plane, and we need to convert that to polar, and we know that dA corresponds to r dr d theta, and x corresponds to r cosine theta. And actually we can rewrite r times cosine theta times r as just r squared cosine theta. So r squared cosine of theta. So now we need to set up the boundaries of integration. So we focus our attention on the inner integral and we ask our inner integral questions. We notice that the inner integral currently is set up to integrate first with respect to r, which means that we are treating theta as a constant. So fix a value of theta. So that manifests as a ray emanating outward from the origin. Okay, and so imagine as we are traveling along this ray, where do we first intersect the region? So right here. Where does the slice start? Here. And then where does it end? Here. So at what r value does the slice start? Well, we said earlier this is the circle of radius 10. So at what r value does the slice start? Well, r is equal to 10. And then where do we stop? R is equal to 20. And I want to point out that our answer to this question does not depend on where we drew our ray representing our fixed value of theta. Here, the intersection point is with the circle of radius 10, r is equal to 10, and the end point, the end of the slice, is with the circle r is equal to 20. And you can see that this would be the case no matter which ray emanating outward from the origin that intersects this region that we used. The slice would always start at r is equal to 10 and end at r is equal to 20. So now let's ask our outer integral questions. What is the theta value of the first slice, and what is the theta value of the last slice? So remember, we always proceed from lower values to higher values for the lower boundary to the upper boundary. And the first slice that we want to take corresponds to this ray emanating from the origin right here, which corresponds to, makes an angle of negative pi over 2 with the positive x-axis. And then we want to keep taking slices all the way across the region until we get to the ray, the slice corresponding to the ray corresponding to, or the ray that makes an angle of positive pi over 2 with the positive x-axis. So in other words, we want to go from theta equals negative pi over 2 to theta equals pi over 2. And there you have it. We have set up this double integral. Now, one suggestion that I am going to make is that since the inner integral, as we've said, is with respect to r, then cosine theta with respect to the inner integral is a constant, which means that you can pull that out. And that might make things a little bit easier. So here's what your integral, your double integral would look like if you treat cosine theta as a constant and pull it out of the integral here. Then what you're left with is a very reasonable looking inner integral. And in fact, the integral with respect to r shows no traces of theta, and the integral with respect to theta shows no traces of r. Then we can actually just write them. This is one of those unusual cases where we can just write them as a product. So it's this single variable integral times this single variable integral. We can't do that very often because usually r and theta, or x and y, are intertwined such that breaking the integrals entirely apart like this is not possible. Usually the boundaries for the inner integral involve the variable that we're integrating to in the outer integral, for example, and so we can't disentangle them like this, but here we can. And so we've essentially reduced this to two single variable calculus problems with two functions that are not difficult to integrate. So if we take the antiderivative of both of these integrals, the antiderivative of sine theta is, of course, or cosine theta is sine theta, and the antiderivative of r squared is r cubed over 3. And so for sine theta, if we plug in, evaluate it at pi over 2, and subtract the function, the antiderivative evaluated at negative pi over 2, what we end up with is 1 minus negative 1. So essentially, the first integral just becomes 2. And if we do the same operation on the second integral, what we get is 8,000 over 3 minus 1,000 over 3, which turns out to be, let's see, 7,000 over 3 times 2, which is 14,000 over 3. And if we find, I guess it's not strictly necessary to do this, but this turns out to be approximately 4,666.67. Oh, it said round your answer to 3 decimal places in the original statement of this problem on WebAssign, so maybe I should try to be consistent with that. 0.667. Anyways, really the crux of this problem for me was determining how I was going to integrate it. Certainly you could have done this in rectangular form, but I think polar turned out really nicely. You can't argue with how simple it was to evaluate these two single variable integrals. You can't beat that. It really speaks to the need to have a number of tools in your tool belt to tackle these double integral problems. Anyways, hopefully it gave you some good experience with determining which tool to use, and there are a few more problems of this nature coming your way.